Lab for spring oscillations. The purpose of the lab is to analyze and model the motion of a mass on a spring that is both swinging and oscillating. Preview of the results are that the computer model very closely replicates the movement of the actual experiment, since the majority of the forces acting on the mass are accounted for in the model, except air resistance, which is tiny considering the small area of the mass. Concepts used include spring force, Newton's second law, kinematics, where position update and velocity update, momentum change, energy principle, kinetic energy, potential energy, spring energy, oscillation, where T equals to pi squared root m over k. System and surroundings. The system are the mass, spring, and earth, since we're counting the energy for all of these three things. The surrounding is just the air. The procedure for this lab is that first the video is loaded in the tracker software, the length of the spring and the origin was calibrated. The mass was aligned with the point mass, and its motion was tracked over the entire duration. X and Y position was extracted and put into a spreadsheet. The K of the period was calculated using the oscillation spring mass system formula, and by using net force at its initial rest position. The relaxed left of the spring was found. The initial position, initial velocity, and the mass of the ball, which were found from the pre-lecture videos, were plugged into the model. The net force on the mass and the energy of the system were calculated using the Newton's second law equation and the energy principle, respectively. The momentum principle was used to update the mass's position and velocity to simulate the motion of the object. When the program is run, the spreadsheet is uploaded of the actual experiment to compare the simulation to the actual motion. Here, the track of results. The spreadsheet data and the tracker graphs received from the tracker are down below. Here you can see the X and Y position of the mass and the X and Y position of the mass compared to the time on the graph. It shows the oscillating motion of the mass. Here's the code for the Python model made, where initially we set the ball's mass, the position, and velocity as the basics, and the ball's velocity is initially 0. Then we take g equals 9.8. K is calculated by using the 2 pi of root m over k equals period equation, where k is isolated to get the k, and the period is calculated by looking at the data in tracker and counting a number of oscillations and the time it took for the number of oscillations and getting the time for one single oscillation. And also then relaxed under the spring is calculated by using the net force on the uh, mass at the start, where it's just the force of gravity and the spring force and it's at rest, where the LO is isolated to get the answer, just pull 103. And then the energy formulas are used to set the initial energy of the mass. Continued code is where in the loop the force on the mass by gravity is calculated by ball dot mass times g, and the force of spring is calculated by multiplying minus spring constant times the s times L hat to get the spring force, and then the net force is done by adding the spring force and the force of gravity. And then the momentum principle and kinematics equations are used to update the velocity and position of the ball. And the springs is updated by using L equals ball position minus the spring position, and L hat is equal to L divided by mag L, and S equals magnitude of L minus L L. And also the energy of the mass is updated as the kinetic energy, the potential energy, the energy, and the deltas of each of them, and to find the total energy, the total change in energy. Here are the results. In the graphs received from the model, we can see that the x and y position of the simulated mass is only a small bit off from the actual x and y positions over the time, and we can see that the energy uh, remains constant, the delta energy remains constant, and it remains in balance. Conclusion: the lab successfully modeled the two-dimensional motion of a oscillating spring mass system. The computational model predicted the trajectory matched with the experimental data from the tracker, validating the procedure. What does it mean? Question. The energy graphs for the mass spring system confirmed the energy principle, as the change in total energy remained effectively 0, as I showed before. And the period predicted for by using just the x movement is 1.6 seconds. The done by y coordinates is 1.55 seconds. And since the motion of the x-axis is like a pendulum, while on the y-axis is like a spring, there's a discrepancy in the results, but they still yield the two very close values. Thank you.